Graphs. We've been looking at graphs, right? All right. Graphs. Graphs of y equals sine t and cosine t. These two are simple shift of left and right, right? So if we use this for a motion, what kind of motion? Harmonic motion. It's not fundamentally different, right? It's a shift. Amplitude and frequency is kind of the same. If you take the quotient, you have tangent t, right? Good. And that's not quite harmonic motion, but algebra, it relates this tangent to, and we sketch those things. All right, I asked you to memorize this one, and then there's two more things that you have to memorize about this thing, and then just why is this asking us to keep memorizing this thing, is that it's not for the test. My motivation on this one is that this world that we're describing, the physical world we're describing using mathematics, in microscopic level, things are understood in terms of vibration, right? Things are vibrating, quantum mechanics and string theories. This is about vibration. Things are vibrating that looks like harmonic motion, right? This is a fundamental element, the mathematical element, that helps to describe the microscopic physical nature. So whatever is happening in between mathematically is a part of the natural law that we're looking at. So why not learning and absorbing some part of the laws of nature, right? So here's a fundamental element. You will see some application. But let's start with writing, actually sketching all these three things you have practiced. So go ahead and write down, xy coordinate, sketch the xy coordinate plane. And especially for sine and cosine, it has to be a little bit stretched horizontally, right? And try to be accurate as possible, especially unit. 1 unit should be close to pi over 2, something like that. So go ahead and sketch all of these with amplitude lines and everything, reference points and all that. So here I've already sketched the sine part. This is starting from 0 to 2 pi. This is 1 period. So let me write down period here. Period being 2 pi, right? This is the time interval where it repeats the complete motion, going up and down. 0 pi over 2, pi, 3 pi over 2 pi. These are reference points, amplitude line up there, y equals 1, y equals negative. Right? So do the same thing for the cosine. Right? This is my cosine, right? It's supposed to be a little shifted image of it. And notice that I'm not stopping at the end of the period. I'm continuing, and using the arrow indicates it keeps moving like that, right? Tangent was a bit different, right? So let me write this one down first. This is y equals cosine t. And what's the period of this cosine t this time? It's the same, 2 pi, right? But what was the period of a tangent? It's different. It was a pi, right? What were the two lines that shows up as a vertical asymptotes, right? What are those coordinates? T equals pi over 2, negative pi over 2, all right? Go ahead and sketch that tall line and see if we can construct that tangent curve as well. So here's my two vertical lines, and the graph is not going to touch this one, right? But it's going to get asymptotically close to that. What were those 3 reference points? One was 0. Tangent is y coordinate divided by x coordinate. So at 0 radian, it's 0 divided by 1. It's 0 here. And we use a 45 degree as a reference point. 45 is right in the middle here, pi over 2, right? Pi over 4. 45 degree tangent value, anybody remember? 45 degree tangent value? 1, right? The isosceles and adjacent is the same. We draw that triangle in your mind. 1 is slightly bigger than pi over 4. Slightly bigger, so I would put it right up here. That's the point right there, right? And negative pi over 4 is, think about negative 45 degree, and the, what is it? Slope is a negative 1, so it's going down there. And those are the 3 reference points we choose. Don't just put the straight line. You have to bend around so that when you approach pi over 2, what happens? Doesn't touches it, but asymptotically getting close to that, just like that for asymptotes in irrational functions, right? And the other one bends around slightly this way, like this. Okay? Work on this one. When you sketch these three things, you got to work on that curvature a little bit. You know, don't try to do that in one stroke. Look at the bit part and do that part, and here correctly represent this curvature. And it's important for the next part, all right? So there's a 3 parts, 1 question. This is the first part you do. Sketch all y equals cosine t and sine t and tangent t. Good? Next part is part toward to the inverse function. Think about inverse function. When you do the sine inverse, if I give you, for example, let me do that as a side in here, side item. Let me make sure think about what this inverse thing is. Inverse is not a reciprocal, remember? Right? What is the reciprocal of sine? Cosecant. What is the reciprocal of cosine? Secant. They have different name for that, right? So sine inverse is not the same thing. So sine inverse represent what? The whole thing represents angle, right? So this whole, if you write down sine inverse of 2, don't touch the calculator. Sine inverse of 2 is the whole thing represent the angle for which the sine value is what? 2, right? That 2 came in inside. Now you go to unit circle, find the angle for which the sine value is 2. Do that in your mind. Go to the unit circle, find the point where the y-coordinate is 2, and then think about that angle. So this whole thing, let me repeat that again. This whole thing represents the angle for which sine value is 2. That's how you read it. So go to the unit circle and figure out the angle where the sine value is 2. Unit circle. And sine value 2. Unit circle, all the coordinates in between 1 and -1, right? There's no way it's going to reach 2. So what's going to happen if you type this one in the calculator? Undefined and error and things like that, all right? What if I change this one to 1/2, sine of 1/2? And there will be an angle, right? How many angle in between 0 and 180 degree? Or 0 and 136 degree? 360 degree, that's what I meant. 2 angles, right? 2 y, you know, if you put horizontal line, that's the y coordinate that always across these 2 points, right? Except the north and south pole. So the calculator only gives you the 1 angle, right? They figure the other thing. That 1 angle now, in terms of graph, has a name. It's called principal branch cut. This is the official name. So I'm going to write that down. So that's what we're going to do. Principal branch cut. Then this is going to be part 2 of this question. And then somebody may call me, Dr. Chang, what do you mean by principal branch cut? And then I'll say, you're supposed to know this, right? That's the part B question. All right. So this is going to be just a part of the graph. That's what it is. So I'm going to copy that sine graph there. So for sine, which angle does it choose? The calculator choose? Positive 90 degree to? That will repeat the sine value, right?
Yeah, but it's going to pick from that top end, and then the principal branch cut will be the
Bottom part. So it goes like this. So I put this y, it's a good description. So I'm going to put it in the middle. So I was wrong. I'm going to put that y-axis in the middle. Sorry about that. And if you go, this is a 1, and pi over 2 is slightly bigger than 1. So pi over 2 is here, right? This is 90 degree, right? If you go up to here, the graph looks like this and curves around, right? And it continues, but we don't go, you just put in a dotted line. We throw that away because it begins to repeat, right? So you stop it at 0 to 90 degree and go to the backward here, negative pi over 2, and realize that goes to denominator like this, right? Does that make sense? All right. So if you just look at negative 90 degree and positive 90 degree, sine value go from negative 1 to positive 1 without repeating this value sign. So calculator will give you angle in between negative 90 degree and positive 90 degree, right? That was the discussion. Now this, we just cut that part and then here, and throw that away. And just focus on that part. And this part is called what? Principal branch cut. Negative 90 to positive 90 degrees. Now, by doing that, before, y equals sine t wasn't a one-to-one function. That was exactly the observation. If you look at one value in here, there are multiple angles, not one-to-one. But now, if you just cut it out, just focusing in here, it's a one-to-one function, right? All the values, there's a unique angle associated to that. So I'm going to the cosine. So principal branch cut of sine is between where and where? That's the correct thinking, but now in the official term is now between negative pi over 2 to pi over 2. That's the principal branch cut of sine of real numbers, not angles, all right? But we think of in terms of angles. How about cosine? In what range cosine value, which is represented by x, does not repeat? 0 to pi, 0 to 180 degree, right? So if you go 0 to 180, you will see the function value doesn't repeat. So here is 1, roughly here is a pi, and here's a pi over 2. And it starts from there and hits there, and go down like this, and continues, but we don't continue with the solid part. We throw away the rest of the part, right? Between 0 and pi, 180 degree, right? This is a principal branch cut of what? Cosine t, right? Good. And do you verify from the picture this is one-to-one? Do you agree? You put the horizontal line, it always only intersects only one point. Given value, there's only one angle. That's the equivalent statement. Good? 1 and negative 1, thank you. Here's 1 and negative 1, this envelope. Any other clarification, question? Then let's move to tangent. Tangent is, I'm only showing the part of the tangent graph, right? What happened to the right and left? You have infinitely many copies of this one, right? And what is the period in here? I think Joshua said that correctly. Period here is pi. Right coordinate minus left coordinate. Pi over 2 minus parenthesis negative pi over 2 becomes pi. It repeats forever to the right and left, right? Tangent is represented by the slope. Where is the slope repeats and doesn't repeat? Think about in terms of quadrant. Right, first quadrant and the fourth quadrant, does the slope repeat? Doesn't repeat, right? But if you go across any other thing, it begins to repeat. So we chose only the first and fourth quadrant, right? So that's negative 90 to the positive 90. The one that we're showing is the period part is already a branch cut, right? So to throw away the rest of the copy and take that is the branch cut of a tangent. Does it look like a one-to-one function? Put the horizontal line, and that's our branch cut. All right? That's a part 2 of the one question in the mock test, right? What's it going to be third? What is the third one going to be? The reason we changed it, cut it into a one-to-one function is to consider inverse function, all right? And I showed an example of inverse in here. Inverse is not the same as reciprocal, right? It's not the same. So deal is that when you do the branch cut, I'm going to spell out all the instruction there. We're going to write down this coordinate. That's very important part. Write down this coordinate. What is the coordinate here? Pi over 2, comma 1. And this one, write that down, 0, comma 0. And this one in here, negative pi over 2, comma negative 1, right? So why don't you go in and write down, since this itself is a branch cut, and you have sketched the branch cut, the cosine, principal branch cut, go in and write down all the coordinates along these 3 reference points. And there is another 3 reference points for tangent as well. And go and do that. All right, you all did that? Next thing is accurately sketching the inverse images of these 3 reference points for each case. That's going to give you an idea of how the sine function looks like. All right? So what is the inverse? It's easy to describe, just reverse an input and output relation, right? X comma y becomes y comma x in the graph. It's easiest to say that, but there's no usually formula. That's why you have a key sign inverse in the calculator. Either formula is so complicated or it's impossible. The fact is that it's impossible. There's no finite process, then you get the exact value of the sine inverse. So it's a transcendental function. All right. But when you sketch it, all you do is that when you look at pi over 2 comma 1, that means your input is pi over 2, your output is 1. That's what it means, right? Inverse function, it flips it. 1 comma pi over 2. Right? That's going to be the shape of the graph. So pi over 2 is slightly bigger than 1, right? So kind of exaggerate that. So 1 is significantly smaller, just like I did it here, right? So pi over 2 goes up there, 1 goes down there. So I'm going to show you how to do that with the sine part. So I'm going to write down principal branch cut of y equals sine t here. And I'm about to flip the inverse of sine t. So here I'm going to copy that vertical axis and horizontal axis in a different. They're labeled the same when you sketch it. So this reference line and reference point, 1 is there, right? It becomes horizontal. Everything switches its role. So 1 is over here with a bit of exaggeration. Here's 1. And pi over 2 is slightly bigger, right? So I was wrong. 1 should be smaller here. Pi over 2 is slightly bigger than 1, right? So I'm going to exaggerate it here. Pi over 2. Everything flips. 1 and negative 1 was on the vertical. Now he's horizontal. And pi over 2 and negative pi over 2 was on the horizontal. Now it becomes vertical, right? Everything flips. Now that point, that was over here in the corner, right? Goes to that corner. So what is the coordinate of here? 1 comma pi over 2. Pi over 2 comma 1 becomes 1 comma pi over 2. That's going to be the input and output under what function? Inverse function, right? Inverse function. All right. So that rectangular corner down there is going to be what is that going to be? Negative 1 pi over 2. Minus, right? The hard part is that how you're going to, so this guy stays here, 0 comma 0 is, if you flip it, still 0 comma 0. All right, when you go to the next reference point under sine, it's kind of go up and kind of decrease it down. And here, you have to go under and approach it in here. And representing this curvature or concavity is important. You practice for the test, all right? If this one is a belly down and belly up, if it's wrong, and you will get markup. You have to sketch this one correctly. Don't make it like almost a straight line so that I cannot distinguish. You have to exaggerate this one, like a parabola, all right? And the other one is kind of going down like that. All right? That's the flip of this thing. Make sense? It's the graph of y equals sine inverse t. So we're going to do cosine. It's also very tricky, so I'm going to do that with you together. And I'm not giving you enough time for you to practice today here, but the same problem, exactly the same problem will appear in the test. I hope you will successfully practice yourself. All right, let's do cosine. You agree that cosine is kind of horizontally stretched, right? Here's 1 unit. You cross 3.1 units, right? If you flip it, it's going to be vertically stretched apart. So when you prepare the coordinate system, you will consider that part. T is here, and the vertical part goes up there. See what I'm doing? Cosine, thank you. That's right. Inverse of the cosine. So we're about to sketch y equals cosine inverse of t. So since you're doing all that, you have the information right up there. The first thing we did is that you look at these all the reference point in x horizontal and vertical axis, and you flip it, right? So what is the information in the horizontal axis here? 1 and negative 1, right? 1 and negative 1. So I think it's roughly about here. 1 and negative 1. You go ahead and mark those, 1 and negative 1. And what are the horizontal part? In the original, it's 0 and pi over 2 and pi, right? That appears in the vertical. 0, and here's a pi over 2 and pi up there, right? Maybe this rectangle thing will help you. Kind of give you the boundary and kind of Shows you how things happen. All right, I want you to look at this point, 0, 1. What happened to 0, 1 under inverse? 1, 0. So you go ahead and put that point here. You see, this is my 1, 0. It came from 0, 1. That's what happened to the input and output to the inverse, right? Where's the second point? Pi over 2, 0, right? Where does that go? 0, pi over 2, that's right here. 0, pi over 2, and then you're going to write that coordinate right here. 0, pi over 2. That came from pi over 2, 0. What is the third reference point? Pi negative 1. Where does it go? Negative 1, pi right there, right? Negative 1, pi. You write that coordinate down. Hard part is, again, sketching with a correct concavity, right? So kind of when you started here, kind of, oh no, it's concave down. This is concave down, but it's still concave down here. So you have to be like this. Right? And then you go like this. I think the cosine is a lot harder. But one thing I do after I sketched it, and you want to make sure you sketch the concavity correctly, right? And this is what you're going to do. You take your paper like this, and then rotate it around, right? Not the shearing. Rotate it. Where's your rotation? Not that rotation. Rotate around 90 degrees. You can do that with your paper, right? Sketch it, rotate around, and it's supposed to look like this, which is inverted, reflected image of original cosine branch cut here. Does it look like it? If you did it successfully, the curvature, this one will be the reflection image of across the y-axis. Do you agree? Yeah. That indicates that you did it correctly. All right? And then put it back to the correct orientation. So let's go back in here, right? Don't you love these tools? I love it. So that's the answer. And after you practice a couple of times, especially the curvature part, I'm sure you'll get it. All right? Make sense? Good. That's our cosine invert. What's the third one? Tangent. Tangent is originally stretched vertically like this, right? And if you flip it, it's going to be stretched horizontally. So consider that when you sketch this x, y, ty coordinates in here. Relatively shorter. They have to be too long. Make sense? Like that? So what was an important part of this tangent graph is the vertical asymptotes, right? What's going to happen to the vertical asymptotes on the reflection? Because horizontal asymptotes, right? That's what's going to happen. So I'm going to put that over here. Now it's the horizontal asymptotes. What was the coordinate of horizontal asymptote here? Y equals pi over 2, right? Pi over 2. Bottom there, y equals negative pi over 2, right? All right. So all the vertical marks, horizontal marks become the vertical, and vertical marks becomes horizontal, right? So what goes to the horizontal pattern here? That comes from the original. 1 and 1, right? 45 degrees. So 1 is roughly here with a bit exaggeration. Then horizontally, originally the horizontal part is a pi over 4. That goes to vertical, right? So here's a pi over 4. Here's a pi over 4. And that gives this 2 points right there. Right? So that's what's the coordinate here? Pi over 4, negative pi over 4. So the pi over 4 comma, no, not pi over 4. So 1 comma pi over 4. Flip it. And what about this guy? You'll write down underneath it. Negative 1 comma negative pi over 4, right? Write down the coordinates. The hard part is, again, sketching this one with the correct concavity. The idea is that you start from 0, 0, you approach that horizontal asymptote. So I think the natural way is that you have to bend around like this. I think that's the natural way to approach horizontal asymptote, not touching it, right? And the other one is pass that reference point and asymptotically approach this thing. So that's the answer. You can do the rotation trick again, right? You flip around, rotate 90 degree, then you should be able to see the tangent, original tangent graph is reflected across the y-axis. That's how you check it, right? So that's the final part of this question. Why is it so important? That again, this is the part of the nature. This is the element that describe that vibration of our microscopic nature of this world. How about this inverse? Why is it it's important? Turns out, when you calculate lots of things, the equation has no transcendental part. In physics and engineering, equation you are staring at it has no transcendental part. It's just t squared plus 1 divided by 2, something like that. But when you're calculating the areas and integrating stuff, which is part of the calculation we did, I'm going to explain why you integrate later. But this guy shows up as an answer. In differential equation, purely algebraic equation, this answer involves sine inverse and tangent inverse. And you better know how this one looks like. So this is it. That's the only part I'm going to cover in that graph of inverse part. No shift of anything about inverse. Just these 3 things appeared exactly as it is. And you have written down this much of information. You see, it took 30 minutes to go through all that, right? So, but you got 10 minutes in the test to reproduce this whole thing. All right? So that's the end of the graph part. And I plan to cover